Unit 5, heat transfer. In heat transfer, there are different modes of heat transfer. So what is in the heat? Heat is nothing but energy transfer due to difference in temperature is called heat. Okay. The modes of heat transfer are conduction. One is conduction, the second one is convection, and the third one is radiation. Okay. In further classes, we'll look into these conduction, convection, and radiation in detail. Now we'll move on to what is meant by a resistance concept. Okay. Actually, the conduction law was given by Fourier, J.B.J. Fourier. It was proposed in the year 1822. Okay. What he said was the conduction, okay, the heat conducted is directly proportional to the temperature gradient dt by dx. So this is called as temperature gradient. Yeah. In order to remove this alpha, so the proportionality, it is given by minus k dt by dx. Okay. Now this k is called as the constant of proportionality, or it is a property of material through which the heat propagates. So this k is nothing but a property of material. A material through which the heat propagates. Okay. Now here the Q will be the rate of heat flux, which is Q is nothing but rate of heat flux, which is watts per meter square. Okay. And this property is called as thermal conductivity. Now with respect to the Fourier equation, we have Q is equal to minus K dt by dx. Now in order to find the temperature difference, so let us take this as a slab or a material through which the temperature is going from here to here. The total length of the material is L, and the temperature at the beginning is T1 and the temperature at the end is T2. So we'll integrate to integral 0 to L dx is equal to minus k integral T1 to T2 dt. Now this becomes Q into X 0 to L minus K into T divided by T1 T2. There it becomes Q equals to Q into L minus 0 L. So minus K T2 minus T1. So that the equation becomes K into T1 minus T2 divided by L. This is the rate of heat flow through a material. This is one-dimensional heat conduction. Okay. This equation is given as one-dimensional heat conduction. We will move on to the next one. Now what is meant by the resistance concept? Similar to that of a circuit, in current we have V is equal to IR, or the current flowing through a particular coil is I is equal to V by R. Similarly, in case of heat flowing through, we have an equation Ka into T1 minus T2 divided by L. This equation can be modified into T1 minus T2 divided by L by Ka. So this L by Ka is denoted as Re. So this is nothing but a conductivity thermal resistance offered by the material for resisting the temperature flow. This is conductive resistance offered by the material. Okay, this is nothing but the temperature. In case of current, we'll have a resistance. In case of any material which offers resistance to the heat flow, or E is given by L by Ka. Okay. Now we'll move on to the composite walls. Composite walls. So in a composite wall, we can see from the diagram there are three. The wall is made up of three materials. So material 1 with conductivity as K1, and with material 2 conductivity K2 and corresponding K3 for the material 3. And each material is of different length, L1, L2 and L3. Hence, the resistance offered by the first material, will be R1 is equals to L1 by K1A, R2 equals to L2 divided by K2A, and R3 equals to L3 divided by K3A. And we could see that all these walls are in series. They are not parallel to each other. Hence, this rate of heat equation can be written as Q is equals to the initial higher temperature is at T1 and the final temperature is at T4. T1 minus T4 divided by R. So the total resistance offered by it will be T1 minus T4 divided by L1 K1A plus L2 divided by K2A plus L3 divided by K3A. Fine. This is the heat conductance or heat conduction, the rate of heat conduction through a composite wall which is kept in series with each other. Okay. This is the physical system. This is a physical system. So for a heat conduction by a wall kept parallelly, we know that the resistance for wall 1 R1 is equal to L1 by K1A, and R2 is equal to L2 by K2A. Since it is parallel, we know that R is equal to R1 R2 by R1 plus R2. So on solving this equation, we get here the length is same, so L can be taken out in common. Qk is equal to T1 minus T2 divided by R, which is equal to T1 minus T2 divided by L into K1A1 plus K2A2. So this is the corresponding rate of heat conduction by walls which are kept in parallel to each other. Now we'll move on to the other physical system where we have a question of both series and parallel physical system. Now we have a material which is composed of both parallel and series combination. Okay. Here the material K2 and K3 with conductivities K2 and K3 which has length L2 is equal to L3. Here length L2 is equal to L3. L2 is equal to L3. Here the resistance offered by the total resistance or the conductivity resistance which is offered by the overall material is equals to L1 divided by K1A1 plus L2 divided by K2A2 plus K3A3 plus L4 divided by K4A4. Hence, the overall rate of heat conduction Qk is equals to T1 temperature 1 minus temperature 2 divided by RT. This is the rate of heat conduction by walls which has got both series and parallel combination. Now heat is conducted in two different mechanisms. One is migration of free electrons, and second one is lattice vibration. K1. So this is how heat is conducted in solids by these mechanisms. Okay. Now lattice vibration indicates the atoms in the periodic lattice arrangement, whether it is FCC or BCC, the atoms are arranged in a manner, and because of vibration of such atoms will result in transfer of heat. And migration of free electrons indicate that free electrons present in an atom migrates from the lower level to a higher level by getting the heat, and it will transfer the heat from one electron to the other electron. Once the electron loses energy, it comes from the higher level to the lower level. Okay. Now for a heat conduction through a cylinder, the equation is given by integral T1 to T2, integral T1 to T2 dt is equals to R1 to R2 and minus Qk divided by 2 pi k L into dr by r. The area of the circle is 2 pi r, hence we put kl into area is equal to 2 pi r. For integrating, we will put dr by r. Okay. Once we integrate this equation, what we get is T2 minus T1 is equals to Qk divided by 2 pi kl ln of R2 divided by R1. Hence the rate of heat conduction Qk is equals to 2 pi kl into T2 minus, or we will take T1 minus T2 because I have left the negative symbol over here which goes there until the symbols will interchange, divided by Ln of R2 divided by R1. So that is the rate of heat conduction through a hollow cylinder. The final equation Qk is equals to 2 pi k L T1 minus T2 divided by ln of R2 divided by R1 for a heat conduction through a cylinder, through a hollow cylinder. Now for a heat conduction through a sphere, a thin spherical strip or the radius of R and thickness dr. So here the heat conduction Qk will be Qk equals to 4 pi k into T1 minus T2 into R1 R2 divided by R2 minus R1. Just memorize all the equations so that you can solve it in the problem which is given in 2 marks. Now we will move to what is in the convective heat transfer. Okay. So what is a convective heat transfer? Convective heat transfer. So what is meant by convective heat transfer is that it involves mass movement of fluids. So when there is a temperature difference, when we have a temperature difference, this results in density change. There is a change in density. Hence, because of density change, there is a movement of mass of the fluid. Okay, and this process is called as natural convection. So we have seen natural convection takes place when we dry our clothes in sun. நம்ம வந்து clothes எல்லாத்தையுமே வந்து வெயில்ல போட்டோம்னா நமக்கு natural convection வந்து ஏற்படும். சரிங்களா? அதே மாதிரி ஒரு mass motion of the fluid ஒரு external pump மூலமா compressor ஒரு blower ஒரு fan மூலமா நம்ம convection, that is நம்ம துணியை வந்து fan மூலமா காய வச்சோம்னா it is called as forced convection. So forced convection takes place with the help of pump, fan or blower, compressor, etc. Okay, so this is called as forced convection. Now in case of convective heat transfer, the rate of heat transfer Qc equals to minus Kf into area T infinity minus Tw. There is surface of Tw is surface at the wall. T infinity is the surrounding temperature and delta is the thickness of layer. Delta T is the thickness of the film or thickness of the layer through which the fluid is getting convected into air. The heat is getting convected. Okay. In case of there is a coefficient called surface coefficient or film coefficient which may be defined as Hc. Hc is called as Kf by delta T. Hence, the rate of heat conduction through convection is equals to Hc A into Tw minus T infinity. Okay, this is nothing but the surrounding temperature. This is wall temperature, or the surface temperature is called Tw. So this one Hc is called as film or surface coefficient of heat transfer. Surface coefficient. Now the thermal resistance offered by the fluid film, thermal resistance Rc is equals to Tw minus T infinity divided by Qc. This in terms of Kelvin per watts. Or it is 1 by Hc. This is the resistance offered by the convection, thermal resistance offered by the fluid film. Now we will look into what is meant by combined conduction and convection and how the formula comes for the combined conduction and convection. In case of combined conduction and convection, the temperature flows through a medium and it comes out. Okay, here the convection takes place at the outer of two surfaces of the medium, which has a thermal conductivity K, and hence the resistance offered by such medium, where conduction and convection takes place in combination. So the resistance will be in series, hence the total resistance will be 1 by Hc, and this one is 1A plus 1 by, or the distance, sorry, the length is x divided by L by, sorry, it's not L, it's K by A plus 1 by Hc2, the thermal coefficient Hc2 A. So this is the total resistance offered by the medium as well as the surrounding temperatures. Hence the rate of heat conduction Qc, conduction and convection, takes place T hot minus Tc. It is nothing but, this is nothing but temperature 1, this is nothing but temperature 2 divided by the total resistance R. Now the next problem is 3-layer composite wall with convection over both exterior surfaces. So here we have three materials with conductivity K1, K2, K3. Okay, their conductivities are K1, K2 and K3. Here the overall heat resistance, the heat resistance offered by it will be R is equal to 1 by Hc1A plus L1 K1A 1 plus L2 K2A2 plus L3 divided by K3A3 plus 1 divided by Hc2A. This is the overall resistance offered by the material, and the heat conduction through convection and is given by Th minus Tc divided by R. This can also be written as UA into Th minus Tc. Now what is meant by U? U is known as overall heat transfer coefficient. This is given in terms of watts per meter square Kelvin. Now next is radiation heat transfer. So for radiation heat transfer, Q is the total radiant energy. So all bodies radiate heat, the phenomenon which is identical to the emission of light. This phenomenon, okay, the radiation phenomenon is similar to that of emission of light. If two similar bodies are isolated together in a vacuum, they radiate heat to each other, but the colder, in two bodies, whichever is colder. So, cold down body now, it will receive more heat, okay, and thus become heated. If Q is the total radiant, energy, so some part of energy will be absorbed, so that is QA, and some are reflected, that is QR, and few are transmitted throughout the body, that is QC, which is nothing but is equals to Q. QC or QT, transmitted energy Q. Now QA divided by Q plus QR divided by Q plus QT divided by Q is equals to 1. Now this fraction is known as absorptivity. And this one is known as reflectivity. And this one is known as transmittivity. For an opaque body, now the transmittivity is equal to 0 and alpha absorptivity plus rho reflectivity is equals to 1. And for solids, most solids are opaque in nature. Okay, by increasing the rho value with surface polishing, alpha can be decreased. Okay. And now a body which absorbs all incident radiation is known as a black body. What is meant by a black body? A body which has the tendency to absorb all incident radiation. Absorbs all incident radiation. So ஒரு பாடியாக இருந்து அதோட இன்சிடென்ட் ரேடியேஷன் அதுக்கு வரக்கூடிய எல்லா ரேடியேஷனும் அப்சர்வ் பண்ணுச்சுன்னா அது வந்து என்னதுன்னா பிளாக் பாடி. ஸோ பிளாக் பாடியை வந்து இட் இஸ் ஆல்சோ தி பெஸ்ட் எமிட்டர் அப்படின்னு சொல்றாங்க, எமிட்டர் அப்படின்னு சொல்லக்கூடியது. சரிங்களா? Now emissivity factor. Emissivity factor. Epsilon is equals to actual radiation of gray body divided by radiation of black body at given temperature T. Now the rate at which energy is radiated by a black body at absolute temperature is given by Stefan-Boltzmann law. Stefan So this law gives the rate at which energy radiated by a black body QR is equals to sigma A T power 4. Now this sigma is called as Stefan-Boltzmann constant, இதோட வேல்யூ என்னன்னா 5.67 into 10 power minus 8 watt per meter square into k power 4. சரிங்களா? இதே ஈக்குவேஷன் வந்து ஒரு ஹீட் எக்ஸ்சேஞ்ச் வந்து ரெண்டு கிரே பாடிஸ் நடுவுல நடந்துச்சுன்னா சோ அத வந்து எப்படி எழுதுறாங்கன்னா Q1 to 2 is equals to sigma into A1 F1 to 2 T1 power 4 minus T2 power 4. So what is this F1 F2 is nothing but view factor or configuration factor. So in later on session we will look into this configuration factor in detail. Okay. Now combined convection and radiation. So in case of combined convection and radiation, the heat is transferred from a hot body by natural convection and radiation. Okay. Now the heat transferred by a natural convection 2C is given by Hc into A Tw minus T infinity. So that is the first equation. And then by radiation it is given by Qr is equals to sigma A1 F12 So earlier I have said you Tw is nothing but wall temperature and T infinity is the surrounding temperature through which the heat is getting lost. Okay. Now the total resistance offered by the conduction convection process, okay, for the radiant heat transfer RR equals to 1 by HR A1, which is nothing but 1 divided by sigma A1 F12 T omega plus T infinity into T omega square plus T infinity square. That is the total resistance offered by it.